So, good morning, my dear students of fourth semester. Day before yesterday, I could not take the class because of your examination result, some work concerned with your semester exam result out. I went to MU and did some work. So, today we will continue the lecture. So, last time in the last theorem, we have shown B is lambda to the power 2 by n, which is equal to determinant W by determinant W plus Q, where W is the within matrix we call it, and the Q is called the between matrix, if I remember. So to complete the solution of the problem, we have to find the distribution of B under S naught. Distribution of B, the statistic under S naught. So our problem was to find a test for the general linear hypothesis denoted by S naught. And you remember S naught is B1 cap is equal to B naught, where B naught is a P by R1 matrix, given matrix. Okay, so this is the problem we have to solve. So we will discuss theorems and lemmas without proof which will be required to obtain distribution of B. So the proofs have a rigorous mathematical computations which are not very necessary for us as of now. When the lockdown is open, we can discuss on the proofs, proofs of the theorems also. So in theorem 1, first theorem, the distribution of Q under the null hypothesis S naught is Wishart, p-variate Wishart with parameter sigma on R1 degrees of freedom. So this is the first result as a theorem. You note down this, and the proof is also not included. And second, a lemma 1. This is we will refer this lemma afterwards when we require. Suppose W1 follows Wishart P sigma M1 and W2 follows Wishart P sigma M2. Independently then, number 1, determinant W1 by determinant sigma follows the product of x's, where x's are chi-square variates. And number 2, W1 plus W2 by determinant sigma follows the product of xj plus y, where x1, x2, xp and the y are independently distributed as chi-square on m1 degrees of freedom, chi-square on m1 minus 1 degrees of freedom, so on, chi-square on m1 minus p plus 1 degrees of freedom, and y follows chi-square on m2 degrees of freedom respectively. So x1, x2, xp are chi-square m1, chi-square m1 minus 1, so on, chi-square m1 minus p plus 1. And the y is chi-square m2 variates. So they are distributed independently. So this is the lemma. So carefully note down these two results. This one and this one. After that, in theorem 2, let us denote V as VPR1M under H naught. What is our H naught? H naught is B1 is equal to B naught. B1 cap is equal to B naught, or B1 is equal to B naught, where B naught is some given P by R1 matrix. So it has R1 columns. So that is why here R1 is coming, and B under H naught is VPR1M. Okay, no problem. M is the degrees of freedom, P is p-variate, R1 is the number of columns in B naught. So we know B is equal to determinant W by determinant W plus Q prime, and we denote B by VPR1M. So this is here, and now simplification, this numerator divided by determinant sigma, here also denominator divided by determinant sigma. So this is equal to product j goes from 1 to p, xj by xj plus y, because of I think because of this lemma, because of lemma 1. The numerator is this is the numerator here, and this is the denominator. See, this is the numerator, this is the denominator. So from lemma 1, and this is equal to product j goes from 1 to p, jj. xj by xj plus y is put as jj. Under where under h0, x1, x2, xp and y are independently distributed as this. This is from lemma 1. Then bp r1m is distributed as the product of jj's, where jj's are independent beta of the first kind variates. That is beta 1, m with parameters, m minus j plus 1 by 2 and r1 by 2 variates. So this is the theorem. This is what we are supposed to prove actually. So this is a statement of the theorem. P R1M is distributed as the product of these jj's, where jj's are beta 1 variates with these parameters. But we will not discuss the proof as of now. But you know this theorem, statement of this theorem, and from this theorem we derive the case when p is equal to 1. When p is equal to 1, Vp R1M is equal to V, instead of p we put 1 here, so 1 R1. So univariate case, p is equal to 1. Then this is the product we have seen in theorem 2. So when p is equal to 1, so p is equal to 1, this will be a single variable, x by x plus y. So where x follows chi-square m and y follows chi-square r1 degrees of freedom independently. So this we put as 1 by 1 plus y by x. This is simplification, both numerator and denominator divided by x. But we know when x and y follows chi-square distribution, their ratios. So chi-square by m, sorry, x by m is in the denominator, and the y by r1 here. So m, we simply put m by r1 y by x is a f distribution on r1m degrees of freedom under h0. Therefore, from equation number 1, the statistic f is equal to m by r1 1 minus v 1 r1m by v 1 r1m follows f distribution on r1m degrees of freedom under h0, thus giving a test for h0. So in order to understand how this f statistic coming, you simplify this v1 r1m is equal to 1 by 1 plus 1 by x, y by x. So instead of y by x, this y by x with this coefficient m by r1 follows f r1m. So instead of y by x, you put some quantity f which follows this f on r1m degrees of freedom. After that, you simplify with this. So 1 plus f into v 1 r1m is equal to 1. After that, you simplify. Ultimately, you take out f. So f is equal to this m by r1 minus 1 minus v r1m by v1 r1m will come. So which follows f distribution on r1m degrees of freedom under h0, thus giving a test for h0. So this simplification you do, this is very easy. You cross multiply this with this. Okay. So this is the case, this is a particular case when p is equal to 1. We will continue in the next video but other particular cases, and we will ultimately find some broad solutions for the problem, that is the problem of testing general linear hypothesis. So for today, let us do up to this, and on Saturday I will upload another video which will provide you some other particular cases. So this particular case is for p is equal to 1, is a univariate case. Okay, have a good day ahead, stay safe, stay home.